Hello everyone, welcome to today's video. So in the last video lecture, we had discussed about the hydraulic design of sewer pipes, the various parameters, and we have discussed briefly about the self-cleansing velocity and the maximum velocities that are being designed for a sewer pipe. Now, in today's video lecture, we will discuss about a couple of design problems for hydraulic design of sewer pipes. Now, this problem is read as design a sewer to serve a population of 36,000. The daily per capita water supply allowance being 135 liters, of which 80% find its way into the sewer. The slope available for the sewer to be laid is 1 in 625, and the sewer should be designed to carry 4 times the dry weather flow when running full. What would be the velocity of flow in the sewer when running full? So this is the question. So we have what is it that is need to be found out? That is the velocity of flow in the sewer. Okay, this question assume n Manning's constant as 0.012 in Manning's formula. So this question was asked in Engineering Services 1970. So now you read the question carefully. What is the population? Population is 36,000. Okay. The per capita LPCT, what is the per capita demand? 135 liters. Okay, that means 135 liters of water is the demand, water demand for one person in one day. What is the number of person? That is the population 36,000. For 36,000, what will be the water supplied? That is 36,000 into 135 liters in one day. Okay, so now pay attention to this unit. 36,000 into 135 liters is the amount of total liter, total volume of water that is being supplied in one day. Okay, now liters per day, this unit has to be changed to meter cube per second. Okay, that is the unit of discharge or Q max. So this is 36,000 into 135 divided by 1000. Why it is divided by 1000? Because we are converting liter into meter cube. So divide by 1000 into in per day means this will come in the denominator in per one day, and it is q max per second. It's meter cube per second. So in one day, how many seconds is there? 24 into 60 into 60. So this gives us as 0.052 q max. That is 0.0562 meter cube per second is the average water supply. Okay, of water that is being supplied. So this is water supplied. Okay, this is water supplied. Now, but as per the sewerage system in Indian sewerage system, we know that whatever the water is being supplied, 75 to 80%, nearly 80% will come out as wastewater or sewerage. Okay, so you find 80%. This was the water supply. So what is the average sewerage discharge? It is 80% of the water supply. So 0.8 of 0.0562, that is 0.045 cumex. So 0.045 cumex is this is the quantity of water that is coming out in the sewer. Okay. Now this 0.045 that you have found out using this calculation, this is the dry weather flow. Dry weather flow means when no rainfall is occurring. Okay, only sewage is coming in the sewer. No rainfall is occurring, no rainy season, only the sewer part is contributing. So this is, as I have told earlier, this is a combined sewerage system. So it contains of storm water and as well as the sewerage, domestic sewer water, septic water you can say, or wastewater. So wastewater that is being calculated is 0.045 cubics. It is a dry weather flow. That means there is no contribution from the storm water. So this is the only discharge that is being flowing. Now, maximum discharge is given in the question. As you read carefully, it is given in the question that the maximum sewer is to be designed. Sewers are always designed for maximum discharge. That is to carry 4 times the dry weather flow when running full. Okay, so the pipe is running full. We are assuming that the pipe is running full, and maximum discharge will be 4 times the dry weather flow. 4 into 0.05, this is 0.18 cube max. Now, you use this Manning's formula. Another thing that is certain diagram called nomogram. Nomogram is kind of a graph which shows there are the various these ratios are there. Small q by capital Q, small v by capital V, small a by capital A. Okay, this proportionate discharge, proportionate area, proportionate velocity, proportionate diameter. So they have constructed the scales. So if you look into one scale, corresponding to one scale, you can find, if you interpolate, you can find from that graph what is the value corresponding to, if suppose d by d ratio, small d by capital D ratio is 0.5. So from the nomogram, if it is 0.5, go to 0.5, and if you can interpolate, if you can plot a straight line, you will find a value of v by b in that same graph. And similarly, you can find a value of small q by capital Q. Like that, likewise, you can find all proportionate parameters. So that figure or that diagram is called a nomogram. So usually nomograms are available, but sometimes if they are not available, then you have to use mathematical formulas like Manning's formula, q equal to 1 by n a r to the power 2 by 3 and square root of s or s to the power half. Now here it is running full, so we are taking all capital letters. That is why it is capital letters are being used for running full. So q, you know, which is 1.18. N is given in the question 0.012. What is area? Pi by 4 d square. R is, when the pipe is running full, what is the area? Pi by 4 d square. What is the perimeter? Pi d. So R is A by P. So A is pi by 4 d square. P is pi d. So pi by 4 d square by pi d is d by 4. So R is d by 4. D by 4 to the power 2 by 3. S is given 1 in 625. 1 by root 625. And this value is 0.1. So if you calculate this value from this value, it is about 8 by 3 is 0.173. D is 0.31 meters. So this is the diameter of the sewer pipe. Okay. So now you know the discharge, you know the diameter, you can find the velocity. The velocity is from continuity equation, v equal to q by a, 0.18 by pi by 4, d you know this square. So this gives us velocity as 2.39 meter per second. Okay, this is the average velocity when the sewer is running full. This is how you calculate the various design parameters. Okay, this is one question. Next, another question we will discuss, that is, determine the size of a circular sewer for a discharge of 600 liter per second running half full. Assume I equal to 0.001 and n equals to 0.05. So one thing to note here carefully is, see, in all this, in the previous question and on this question also, what is the question, what is the thing that is need to be found out is diameter, size of the pipe. Here it is determine the size means the diameter of the circular sewer. Previous question also we have found out the diameter, and then after knowing the diameter we can find the velocity. Sometimes it might happen that you will be given in the question, diameter will be given and you have to find slope. Okay, what is the slope? So I told you earlier also, in the earlier previous sessions, previous classes also, I have told the design of any pipe, any sewer pipe or a gravity pipe in which gravity flow occurs, the main two parameters, design parameters, will be the diameter and the slope. These are the main two parameters. If you know one of them, and if one of them is unknown and the other parameters are known, you can easily find out using the Manning's equation. So now here diameter you need to find, but given it is half full. So if it is half full, d is 0.5 capital D. So d by d is 0.5. So there is a table, as I told nomogram, about nomogram I told, there is also a table 4.8, where for every corresponding value of d by d, you will get a value of small v by capital V, you will get a value of small q by capital Q, and a value of a by a, like proportionate. For every value of proportionate diameter, you will get values of proportionate area, proportionate discharge, proportionate velocity, all the other parameters. So now here q, small q is given as 600 liters per second, that is 0.6 qms. S, the slope is given as 0.001. Okay, n is 0.005. From that table, if you solve using that nomogram or that table, if d by d is 0.5, then small q by capital Q is also 0.5. Okay, so this gives q is q by 0.5, that is q is 1.2 q max. Now if n is not varying, usually n will not vary, it will depend on the material of the construction, the material of the pipe. So it is not changing, so n will be same. And We know what is the full discharge when the pipe is flowing full. What is the discharge? We have found out this. So using this formula, Q equal to 1 by N A R to the power 2 by 3 S to the power half. Okay. So you put what is, you know what is Q, what is 1 by N is given in the question. What is A? Pi by 4 d square. R is d by 4 to the power 2. S is given. So from this equation again, like the similar question, you can find what is D. D is 1.93 meter. So hence the diameter of the sewer will be 1.93. Now another way of solving this problem is, suppose you are not given this table. You are not that these tables or any nomograms, these are not available. How do you find it? So this is an analytical solution. So what we take is, we know that d by d is 0.15, and again in the formula it is given small d by capital, this is given by small d by capital is given by half into 1 minus cos of alpha by 2. Alpha is the central angle that is subtended. So cos alpha from this d by d is half. So here also it will be half. So this half and this half will cancel out. So 1 minus cos alpha by 2 will be 0. Okay. So cos alpha by 2 will be 0. Alpha by 2 will be equal to 90 degree and alpha is 180 degree. That is, it is half full. So now you know what is the equation, small a d by d square by 4. Yesterday in the last video we have discussed, a is given by d square by 4 pi alpha by 360 degree minus sine alpha by 2. So in this equation, simply put what is the value of alpha. Okay. So d square by 4, here we have put alpha. Alpha is 180 degree. See, we have put this pi alpha sine alpha. We have put, from this equation we get this value as pi d square by 8. Okay. So this is the equation. Now using what is the perimeter? Perimeter is pi d alpha by 360 degree. Again, alpha is 180 degree. So weighted perimeter will be pi d by 2. So what is the hydraulic mean radius? A by P. Pi d square by 8 by pi d by 2. So this gives us as d by 4. So what we get, what is the inference that we are getting from here? In both the cases, whether the pipe is running full or the pipe is running half, both the cases, if you are not, even if you are not given any data, the hydraulic mean radius straight away you can take as d by 4 for solving straight away solutions. Okay. So again, now you know what is R. R is given. Q, small q, you know, is given in the question. N you know, A you know, R you know, S you have to find. R means R is given in terms of D. So from this equation, just put these values. Q is 0.6 given in the question, and N is 0.055, A is pi d square by 8, R is d by 4 to the power 2, S is 0.001. From this you find D is as 1.93. Same answers you will get. Whether you solve from the table or you solve from analytically, answers will be same. So this is one kind. Another kind of a question. So these kind of questions may be given for hydraulic design based on the population, based on your here in both these problems, the stormwater component is not given. Sometimes your stormwater component you have to calculate using time of concentration, using your Reynolds formula Q equal to that we have discussed in the previous sessions, that stormwater component is given by 1 by 36 K into PC into A. A is the runoff coefficient, PC is the intensity, and A is the catchment area. From that formula you can, that is called as Reynolds formula. So sometimes sewerage component will also be given, and your rainfall stormwater component will also be given for Indian conditions. I have told you to calculate. Okay, these two questions we have discussed, and this will give you certain idea of how to solve the design problems of sewer pipes. So that is it for today, and the next class we'll discuss about the sewage treatment, in brief outline of the sewage treatment, and that will complete the fourth unit, and the subsequent classes will start the next unit. So thank you for listening to this video.